Okay, so let's begin. Today we are very happy to have Veronika Hubeny from UC Davis, and she'll be telling us about the holographic entropy cone from marginal independence. Please take it away, Veronika.
Well, thanks very much. Thanks for the invitation, and it's very nice to see everyone virtually. If you want to, I'm looking at your screen, so if you want to communicate that you're looking bored or confused, feel free. Assume that you will stop me to either sort of slow me down or speeding me up, and so I'll go at some hopefully not too boring pace and hopefully not too fast. Okay, so this is based on sort of a bunch of things, a program that I have been sort of intrigued by for last couple of years about understanding the holographic entropy. And this is sort of a progress report. In fact, I came to give an SITP colloquium a few years ago, and that was about sort of the onset of that program. And so the main component here will be on work in progress with Sergio and Max, but also a couple of sort of related projects with various collaborators here. Okay, so the overall motivation, well, is twofold. One is from holography and one is from quantum information. From holography, of course, we want to understand sort of how does gravity emerge from some non-gravitational jewel. And in particular, we have had all these hints that, well, entanglement structure plays a crucial role. So we want to understand what to sort of specify this and sort of extract as much of the sort of lessons and insights from the statement as possible. So one route to this has been sort of understanding the entanglement structure that corresponds to geometric states. So what I mean by geometric states in a holographic field theory is ones that have a geometric dual in terms of a classical geometry. So I should say at the outset, throughout this talk, I'll be working just in the classical limit, large lambda limit of holography, and I won't say anything about sort of quantum corrections. Okay, so the entanglement structure is very conveniently diagnosed by looking at entanglement entropy. And so from the QI standpoint, one wants to understand better what sorts of information quantities are well described from entanglement entropy. Okay, so the plan of the talk is to first sort of contextualize things and then tell you about, so this is all, this part is sort of the previous stuff that already came out, and this is sort of new. So in the newer part, there will be two sort of constructs that I'll talk about, something that I'll call V-space and a PMI, and two useful tools that will allow us to unearth more about this entanglement structure. And then I'll finally get to sort of the upshot, the main theorem. So, of course, you all know about entanglement entropy. I'll be, utilizing, assuming that I can partition the Hilbert space and write a reduced density matrix and correspondingly the von Neumann entropy associated with that. I'm not going to go into any of the subtleties with sort of recasting this in operator algebra language or any such thing. And so I'll take the context, or rather the assumption that, okay, we can specify some n subsystems, typically some n spatial regions in the space on which the CFT lives. Okay, so they each have their Hilbert space, and I can take an ancilla to purify the full system so that I can be talking about sort of the density made a mixed state on this n partitioned Hilbert space or a pure state on this n+1 partition space. Okay, so if I want to consider what entanglement entropies I can have for these different subsystems, I can organize that into a collection, which I'll which I'll view as a vector of subsystem entanglement entropies, where a subsystem can be either one of these individual ones or composite ones. Okay, so as the entanglement entropy of the combined subsystem AB is not determined from just knowing entropies of A and B unless the two are decorrelated. So there's 2 to the n-1 such independent quantities, entanglement entropies of the subsystems that I collect into this entropy vector. And sorry, what did I say in the previous? Okay, and it's conceptually useful to consider as much as refined a subpartition as I can in this partitioning of the space on which the CFT lives. Of course, I can partition it infinitely, and in some sense, one of the emerging lessons is that this is an important part in characterizing what can appear holographically, that the space on which the CFT lives is just a continuum. You can partition it any which way you want, and the relations that we develop work for any such partitioning. Okay, so not all possible collections of entanglement entropies, these entanglement entropy vectors, are realizable physically, and they're subject to various restrictions. So the universal ones that apply for any quantum state are the subadditivity, which is just positivity of this mutual information, or strong subadditivity, which is the positivity of the conditional mutual information, or equivalently, the monotonicity of mutual information. And depending on of course, there are many more. So this is for n equal to 2 specified subsystems or colors. And here this is for 3 subsystems. So if you have more subsystems, you have more such restrictions, and you have further restrictions depending on the type of the system. And so we want to understand specifically the system that appears in the holographic context. So such a set of physically allowed entropy vectors, which live in this entropy space, don't live in the full entropy space, but in what turns out to be a cone, a convex cone, and in fact for holography, a polyhedral convex cone in this entropy space. Okay, so here's a sketch for just 2 parties, and you can characterize this convex cone in variety of ways. The 2 useful ones is by sort of as a convex hull of this extreme rays. Another very useful one is by an intersection of all the half spaces determined by these entropy inequalities. So this is what we dubbed the holographic entropy polyhedron. But the cone and the polyhedron, well, in this picture are identical. It's just a different representation of it. Okay, and we can prove that they are equivalent subject to a conjecture. So we believe they're equivalent, and we have no counterexample, but so far we don't have a full proof that wouldn't rely on a conjecture. Okay, so such a cone of entropy vectors, when you restrict it to the context of holography, is the so-called holographic entropy cone, which was coined already in this Caltech group paper a few years ago. And what is known so far, so if you partition the subsystem into just 2 parts, that's very coarse-grained. And in fact, even though the set of all geometric states in holographic field theory is, of course, vast subset of all possible quantum states, nevertheless, for such a coarse graining, the quantum entropy cone really coincides with the holographic entropy cone, and it's really delimited only by 3 inequalities, the subadditivity and its hierarchically cousins, which are obtained from the subadditivity by sort of purification. Okay, so there's a symmetry, that sort of permutation and purification symmetry that can rotate this around. Now, for larger n, this holographic entropy cone is really a proper subset of the quantum entropy cone. So it's specified by additional inequalities. So for separating into 3 parties, the quantum entropy cone has part that is specified by subadditivity. So there's 6 independent instances of subadditivity, including these hierarchically type inequalities. And what I'm drawing here, this is not the cone. This is not the radial direction of the cone. This is like a cross-section. Now the entropy space for n equal to 3 is 7-dimensional. And so this is like a 3-dimensional cross-section of the entropy space that doesn't include the origin. So you don't see the cone, the radial direction of the cone in this picture. Okay, so there are these subadditivities, and there's also strong subadditivities. And that's it. And that delimits the entire quantum entropy cone for n equal to 3. But for holography, there's a stronger restriction. As I said, the holographic cone is inside the quantum cone. And in fact, these strong subadditivities become redundant and are replaced instead by a single inequality, which is the MMI. So that is this monogamy of mutual information, which is now an inequality that only pertains to, that's true for all states in holography, but not for all quantum states. So besides the positivity and monotonicity of mutual information, which is now redundant, we have this monogamy of mutual information, which is this one written out. Now, curiously, if you prove it using, the original way that Matt and Patrick and Alex had formulated, it's almost identical to the proof that Matt and Tadashi had for just the strong subadditivity, even though strong subadditivity is universal, whereas MMI is not universal. So this geometric proof didn't distinguish the 2 types. On the other hand, if you actually use a different prescription for the holographic entropy, using what Matt Hedrick and Mike Friedman had formulated as the bit threat prescription, then that language is much more conducive to actually distinguish between this type of inequality and this type of inequality. In fact, the original bit threat paper proved this very easily and showed that you can't, with the same set of tools as you prove this, you can't prove this. And so the subsequent way that this was proved actually suggests that this MMI is much more cognizant of bulk locality in holography than SSA. Okay, that was just a throwaway aside. Okay, so that was for n equal to 3. For larger n, well, first of all, already the quantum cone already for n equal to 4 is unknown.
Sorry, Veronika, can I ask a naive question about the inequality that you had? So just the word monogamy, what are the words we would say to justify the use of the word monogamy there? Like,
good.
how
So if you
IAB, yeah.
Right. So if you think of, okay, you can equivalently rewrite this inequality as negativity of the tripartite information, which you can re-express in terms of mutual information. And if the mutual information is monogamous, that means that the correlation between A and BC, well, the correlation between A and B cannot be sort of tapped into by the correlation between A and C, if C is distinct. And so the correlation between A and the combined system BC must be at least as large as the correlation between A and B plus the correlation between A and C. And so that's why it's monogamous. It can't be shared. So this can't have piece of this and therefore be positive. For quantum states like GHZ, which you reduce, which you take a subset of, that would, for example, violate this this MMI. Okay.
Okay.
But that was the language. We have one of the authors of that paper in the audience. So we could call on him to justify the language.
Your answer, you did a great job answering it, Veronika. I couldn't do better.
Okay, fine, thank you. Okay, other questions? Okay, so for n equal to 4, the quantum entropy cone is not known, but the holographic one is known. And in fact, it's delimited still by only subadditivity in this MMI. But now, because there are many more, well, there are more parties, there's more combinations. So there's in fact 20 independent inequalities. And this grows, this number grows. So for 5 parties, we have 5 more inequalities, which were already specified in this Caltech paper and then proved to be complete set by Sergio Hernandez Cuenca a few years ago. And now it actually has, well, these 8 orbits, they're actually 1 subadditivity and 2 MMIs, plus these 5 more. So there's 8 orbits of facets, but that means orbits under permutations. And so how many individual facets there are, there's actually a total of this 372 facets. And similarly, there's like over 2,000 individual extreme rays. Now for larger partitioning, okay, we don't know yet the full holographic entropy cone for 6 parties, but we already know that there are many, many more inequalities. So Sergio and friends have this, are finding more and more as we speak. So as of, I guess, a few weeks ago, there were at least 140 orbits of facets and some 3,000 orbits of extreme rays. And these have very low symmetry. So in effect, you have to multiply this by some 7 factorial to get the number of the individual things. So that gets into millions. Okay, so there's this vast growing complexity of the structure with N. So Ronak, you were going to ask something?
Yeah, so no, thanks. Yeah, so the way I should think of these facets in extreme rays is that a facet is a saturation of 1 inequality and extreme ray is a saturation of 2 inequalities, right?
Of D minus 1 inequalities. So extreme ray is one-dimensional. It's the one-dimensional ray.
Okay. Oh, it's always one-dimensional. I see.
It's always one-dimensional. And the cone is the span of these one-dimensional extreme rays. And the facets are D minus 1-dimensional hyperplanes.
I see. So this is, and this is a very intuitive reason why none of the intermediate objects turn up, because, you know, this is a co-dimension 1 object and a dimension 1 object. And
oh, they turn up. They will turn up in a moment. So the structures that I'll introduce, these V spaces and PMIs, are intermediate dimensional.
Okay.
It's just to characterize the cone, it's easier to either go from the lowest dimensional set or the highest one. You could also characterize it by these intermediate dimensional things. I see.
Okay. Thank you. And is it in fact a cone in the sense of you know, it's a complete vector space with positive coefficients?
It's a subset of the positive quotient.
Yeah, right. Somehow the picture you drew of the subadditivity plus strong subadditivity cone, that didn't look like that, right? It looked like it had a cap.
Let me find myself. Okay, here.
Sorry, yeah, right?
Right. So here.
He's talking about a further one, Veronika, a later picture.
Oh, I see. This.
Yeah, that one, yes. Yeah, that one.
Okay. Yeah. Well, as I said, I'm just going now. This is in 7-dimensional space. I'm drawing some 3-dimensional cross section of it, and the cross section is like in the other entropy space would be like something that does not include the origin.
I see. Okay.
So this would be like the analog of the polyhedron.
Okay.
So these things are the facets. The extreme rays are like the vertices here.
Okay. I see. Thank you.
Great. And in fact, the vertices are, these are the 6 bell pairs. And then there's a 4-party perfect tensor. And then there's the GHZ. So it has a nice structure like that as well.
The GHZ is included in this picture?
No. This was the quantum cone. The GHZ is not included in the holographic one because it got killed by the MMI.
I see. Okay. Thank you.
And in fact, the strong subadditivity is now redundant because you can see it as sort of subadditivity plus MMI in the algebra level. Great. Other questions? Okay. Okay. So
I have one. Did you say that
Okay.
we don't know? You commented on these 2 characterizations of the cone, one in terms of the rays and one in terms of the half spaces, but you said that we weren't sure if they were equivalent. Is that right?
Yes. Well, we think they're equivalent. We don't have a full proof. This is a bit more subtle, so that may be the full discussion of that we can postpone till after.
Okay, yeah, sure.
But if you want to ask something clarifying.
Yeah, I'm curious to hear more about that, but it can wait.
Okay. Great. Other questions? All right, so let's see, let me find myself again. Oh yeah, there was one more point that, okay, so since the cone is complicated, we want to sort of understand not just the inequalities, how to get the inequalities, because after all, each inequality is a multi-line mess. That's not particularly revealing when you just look at it. We want to understand where these things come from, or is there some organizing principle by which we could in principle derive the inequalities explicitly, but what is that principle? Okay, so it's like getting action principle rather than explicit solutions, or even the equations of motion. The action principle is much more revealing. So we want to somehow get at that. We're not there yet. So what I'll tell you about is sort of a step in that direction. Okay. So the original strategy was to, first of all, enlarge the set of quantities under consideration. So these information quantities are things that combine these entanglement entropies into a linear expression with some rational coefficients. And the polyhedron is given as intersection of these half spaces, but we want to consider even the ones that are not necessarily sign definite. But ones which are sort of independent, which vanish for some configuration, but on that configuration, none of the other ones vanish. So we'll call these information quantities primitive. So they can be expressed as so saturating each such quantity being zero, setting each such quantity being 0 specifies a hyperplane in the entropy space, because it's one relation for that poses a restriction on all the entropies. And the full set of such primitive quantities is what we dubbed hyperplane arrangement. Okay, so that was one ingredient. The other ingredient is to utilize holography, where the key feature that we want to utilize is this minimality prescription in the, so we use the RT and HRT prescription of associating entropy of a given region with an area of an extremal surface that's homologous to that region. But in case where there are multiple extremal surfaces that are homologous to the same region, we choose the one that has least area. And this minimality is crucial for everything that we do. And it, in particular, it allows to have sort of phase transitions, quote unquote, in terms of which of these extremal surfaces actually lead to this, whose area has this corresponds to the entanglement entropy. So now the entanglement entropy is infinite when you have when the surface reaches all the way to the boundary, when there is some entangling surface for these regions. And so you can't localize, strictly speaking, the entropy vector of some holographic configuration like this in entropy space, because all the components of it would be infinite. In fact, you can't even localize it on celestial sphere, as it were, of the entropy space, because by changing, well, okay, so you could get some entropy vector by imposing some regulator, some UV regulator, and then counting the area of the surfaces only up to some value. But of course, that value depends then on which regulator you choose. But even the ratio of entropies, like the ratio of A's and B's entropy, depends on what sort of regulator you choose, what function here you choose. And as a limit, when you take this regulator to 0, this is not sort of cutoff independent. Okay, so that's now good. So you can't really localize a configuration like this in the entropy space independently of some extra baggage that you don't really want, like specifying a specific regulator. Okay, so instead what we want to do is, well, we notice that there are quantities, however, that don't depend on the regulator in the least, and that's precisely the saturation of these information quantities, these primitive quantities vanishing. So for example, the mutual information here between A and B, if the AB extremal surface is the one that the smallest area is the one that's composed of these two, rather than what would have been the arch between them, then of course it doesn't matter what regulator you pick, but when you take S of A plus S of B minus S of AB, you're subtracting off the same areas, and so it vanishes trivially. Okay, so we want to make use of that. And so under varying this cutoff, this entropy vector then spans, in general, some lower dimensional subspace of the entropy space, subject to quantities like this vanishing, always vanishing, no matter how you vary the cutoff. And so these hyperplanes and their intersections of the hyperplanes for all the ones that vanish are the sort of more natural constructs. And we want to sort of recast thinking of the entanglement entropy, not in terms of thinking of the value, the actual, numerical value or under some regulator, but as thought of as constructed from these surfaces. So the surfaces take on a useful meaning rather than just something whose area we're evaluating. So this is kind of a new perspective. And in fact, it's slightly radical one, because we don't even need to use the minimal surfaces or extremal surfaces at all to talk about entanglement entropies. We could have used Matt's sort of bit thread prescription or other things, but nevertheless, focusing on these extremal surfaces and dealing with them as objects in their own right, so this is what we're calling these proto-entropies, turns out to be incredibly useful. And in particular, it turns out to be very useful because it allows us to extract a sort of a discrete structure that will suffice to delimit the entire holographic entropy cone.
Veronika, sorry, can I ask a question at this
Yeah.
point? I could have asked it maybe a little while ago, but it's also appropriate here. So when you say holography, you have in mind specifically asymptotically ADS, as opposed
yes.
to, say, the non-conformal branes or, many other examples where it's not that way. So obviously the general results about any quantum system apply regardless, but you could ask this question of, do you get large radius much more broadly than just in these kinds of pictures? So yeah, how much does this rely on asymptotic ADS?
It relies on RT. Anywhere I can use RT or HRT, the prescription of areas of extremal surfaces, everything carries through, because again, I'm dealing with these proto-entropies and extracting the sort of combinatorial structure. So the, the question is bounced back to you, to what extent does RT actually apply in these broader contexts? To the extent that it applies, everything will go through.
Okay, great, thanks.
But I'd love to discuss it more with you afterwards. I mean, again, where all it does apply. So.
Great, thanks.
Okay, so those were the two main lessons from previous work. So now let me go to the new stuff. So first, let me sort of try to specify this structure that I want to extract from a given configuration. All right, so one useful structure is what we call, so far we have been calling V space. V doesn't mean anything, it's just a vector space. We're currently looking for better names of it, and there will certainly be better name of it, but for now I'll just call it V space. Okay, so it's an intersection of all of these hyperplanes in the entropy space where the primitive information quantity vanishes. So it's something that's pertaining to every configuration. Every configuration has a set of these things that vanish, and their intersection in the entropy space is this V space. And the claim is that this captures all the essential features of the full multipartite entanglement structure for that configuration. And it's crucially insensitive to all these sort of irrelevant details of, what would have been the actual entanglement entropy under a specified cutoff and so forth. Okay, so it turns out to be, in a sense, the most refined sort of meaningful, the lowest dimensional meaningful subspace that you could ascribe to a given configuration. And by construction, it has a sort of a discrete structure, okay, which I sort of motivated it pictorially in the previous slides, but I didn't make that explicit. So let me just, for now, leave it as an assertion and re-explain it later if people want. Okay, now this V space is okay, a linear subspace of some dimensionality. The dimensionality, so it's subspace of entropy space. Entropy space has d dimensions. And so this V space can have anything between 1 and d dimensions. So in particular, extreme rays would correspond to 1-dimensional V spaces and facets d-1 dimensional V spaces. Okay, so that's a useful construct. A different construct, which is also a linear subspace of entropy space, is a pattern of marginal independence, which we abbreviate PMI. And this is focusing not on arbitrary information quantities, but only on mutual information. So only mutual information. And we want to specify which mutual information between which subsystems vanishes. So we want to have the full set of these subsystems, I'm calling them X and Y, for which the mutual information vanishes, meaning X and Y are fully decorrelated. Their marginals, which is the reduced density matrices for these individual subsystems, are independent, meaning the reduced density matrix for X, Y factorizes into the X and Y. Okay, so that's why it's called pattern of marginal independence. I want to know the pattern refers to sort of the specification of all of these pairs of subsystems that are decorrelated from each other. Okay, so if you give me an entropy vector, you can calculate trivially all the mutual informations between any subsystem and any other subsystem. You can determine which ones of them vanish. You can take each of these hyperplanes, you can intersect all of them, and you get this PMI, subspace of the entropy space. So each entropy vector has the unique subspace, which again can range in dimensionality between 1 and D. But it's much more primal construct than the V space. It's much simpler, and it rests only on the specification of which systems are completely decorrelated from each other. Nothing more that sort of manifests the multipartiteness in any sort of more direct way. All right. So it's a linear subspace. It also has this discrete structure. And okay, I said this, and because it's given by intersection of all these subadditivity or hierarchically hyperplanes for those that are mutual informations are saturated, and not any other information quantity that would have reduced the V space further, this PMI must contain the V space. However, we don't really know what is the precise relations between them. Are they equivalent or are they not equivalent? Or rather, we do know, and it's not always that they're equivalent. In particular, when you're saturating something else like MMI, the V space is contained strictly as a proper subset of the PMI. Okay, so now I have said PMI, this pattern is just a specification of these pairs for which are decorrelated, but not all such patterns are admissible, are physically sort of realizable. Some are impossible, either because of sort of a mathematical inconsistency or physical inconsistency. What I mean by that, some violate just identities between different mutual informations when you write them out in terms of entanglement entropies. So for example, this sort of equality is just an identity when you write this out. And it comes from the tripartite information being permutation symmetric under all its arguments. And what I mean by physical inconsistency, well, okay, let me say one more thing. So how does this restrict this pattern of marginal independence? Well, suppose that these three mutual informations vanished, well, then automatically it has to be the case that this one vanishes. If it doesn't, then it's an inconsistent pattern. Physically, you also have these relations on the entanglement entropy. So for example, subadditivity would have said that every mutual information has to be non-negative. So if you know that both of these vanish, then it automatically implies that each of these must also vanish, because otherwise you wouldn't be able to get something zero being something non-zero. Okay, so more complicated ones, although it's simpler, is sort of strong subadditivity. So if A is decorrelated from BC, then it must be decorrelated from B or from C individually. Conversely, if A is correlated with B, then it has to be correlated with a larger system BC because of this monotonicity. Okay, so there's many such inconsistencies that one has to avoid to specify this marginal independence. So the marginal independence problem, which is what this refers to, is the question of what such patterns of marginal independence are realizable. And this depends on which systems you're talking about. If you're talking about quantum mechanics, there's more such patterns than if you're talking about holography and so forth. And there's lots of other things. You can talk about classical states, stabilizer states, and so forth. And each of them have their own sort of this marginal independence problem. So it's much more coarse-grained question than a priori. Apparently, it's much more coarse-grained question than asking what is the entropy cone for these types of systems, because it only cares about when are systems decorrelated as opposed to what is the amount of correlation between the subsystems. It never cares about the amount of correlation, just whether they're correlated at all. And yet, in what I'll say, it looks like, nevertheless, answer to this problem, in particular the one for holography, will allow us to determine the entire holographic entropy cone. Despite the
Veronika,
fact
can I ask one more question?
Yeah.
When you say the entire cone, I just want to, that's a wonderful goal, but let me try and understand how much it contains. So you can divide the system spatially as you've been focusing on doing, I think.
Yes.
Or in all sorts of other ways, separating the degrees of freedom internally in any number of ways.
Yeah.
Does doing the latter add conditions that are important also? And is that contained in this holographic entropy cone, or?
No, it doesn't delimit it further because we can realize all the extreme rays. And once we do that, we can realize the convex, anything in the convex hull of them. And so it's basically, if you partition the system, the degrees of freedom in some other way, it itself would also have its own cone. It's not sort of comparable with the one where you partition the system in terms of spatial partitions. Well, okay, let me say something else first, which is every time I say holographic entropy cone, implicitly I'm already telling you that I have partitioned the system into n spatial regions. If I partition the system into some other number of spatial regions, that's not that cone. So already there's infinitely many cones, even for just spatial partitioning. There's on top of that many more cones by some other type of partitioning.
But you could combine them, right? You could take a given spatial region and furthermore divide the degrees of freedom living in there if you wanted to.
But it's not plotable sort of in the same space, because the space is the sort of the, but
I'm just saying we don't need to belabor this if it's not relevant. I'm just saying you could subdivide those degrees of freedom further if you wish, either spatially or not spatially.
Indeed.
And I'm just wondering if you learn more conditions on having a geometric state from that, or if it's somehow redundant with what you're learning just by doing the spatial partitioning.
Very good. Yes, that's an excellent question. I think it's redundant once you utilize arbitrary spatial decomposition. So if you decompose it into fine grain, the space on which the CFT lives, then maybe there's some, it's more complicated than you would have. It's like a Fourier transform in some sense. If you want to say, look
sorry,
at
I have in mind. Yeah, but I mean, in a holographic setting, you also have the additional dimensions, the sphere, if you like, and so whether that looks geometrical or not is a consideration, I would think. So that's part of why it wasn't clear to me. Well,
to the extent that the cone is meaningful at all, meaning it's plotted in entropy space where the axes are specified to be something. In this case, entropies of regions. Now, you could try to extract other Hilbert space, other types of subsystems.
Let's just say the ones that have to do with the S5 or whatever. I mean, in terms of mapping it to the geometry, we could have in mind internal degrees of freedom that we know about in these models. It's okay if it's not.
Actually, I should. Okay, let me think more about that. That's. I mean, my argument that you get everything was just based on saying that you get the entire interior of the cone by taking convex hull of the extreme rays that you can physically realize, and you can't get outside of the cone because that sort of would violate some of these inequalities. But that's still formulated in the context of this these entropy inequalities. So, for example, actually, let me ask the audience, does anyone know if, for example, MMI is something that would have applied to subdividing the system in any other way than spatially, if I mean, along the lines that Eva is saying. So let's take some other, completely other type of approximate factorization of the Hilbert space. Okay, you call the Hilbert spaces by A, B, and C. You write a formal inequality like MMI. Does that thing hold in such a decomposition? Does anyone know? If it doesn't hold, then what I said would not, then Eva, you're completely right. There would be a completely different cone, and this wouldn't inform whether you're restricting more or less. It would just be limited context to the spatial decomposition.
Okay, well, that sounds like at least the conservative answer, so thanks.
Matt, you were going to say that, or?
I was just going to say that I don't know of any reason why MMI would hold for a different way of decomposing other than
Right.
space.
Okay.
But I don't know a sharp counterexample either.
Yeah, I also suspect that if you do some completely different type of, like even momentum space, I'm not sure whether you would, to the extent that it's meaningful.
Yeah, there's momentum space. There's also, again,
There's the internal sphere.
The things that correspond to dividing the internal sphere, where at least you have a geometrical picture. But anyway, I think I've taken enough time with this question.
Okay.
So I should, yeah,
Fine.
but thank you very much. Thanks.
Okay. Actually, let me check. How much time do I have? I've not been.
We are at the 45-minute mark. We started 5 minutes late, so. And we can go like 5-10 minutes late. So we have like maybe 20-25 minutes.
Okay. Okay. Very good. I'll try to get to the crucial part in that. Okay. So, all right. So there's this comment was sort of slightly aside for now, apart from the fact that it will reappear as a step towards finding this holographic entropy cone for this geometric decomposition of the space. Okay. So the tools that we're using, so this is work in progress, but the tools that seem to be very useful for this is sort of the language of not just the hyperplane arrangement and the sort of, it has a poset structure, which in fact is a lattice, but apart from that, to understand, especially this component, it's very convenient to use the language of matroids. Okay, but I won't go any deeper into that. So we're not done yet, but we have a program that looks like we can that we can, at least in principle, solve this problem. Okay, so there were these two spaces that I introduced. Let me now go to the tools that we actually use to work with them. One is just recasting things in terms of graph models, and one is using what I call coarse graining or fine graining. Okay, so the graph models are just a convenient representation to extract away only the combinatorial discrete elements from this holographic configuration. And this was already introduced in this original holographic entropy cone paper. You use vertices to denote every region that's bounded by pieces of these RD surfaces, and you use edges to describe every RD surface. So for example, in the simple picture, this is a boundary space with two regions. This is the bulk direction. This would be the individual RT surfaces. And in the graph representation, you would have three vertices, one for each region and one for the purifier, the remainder. And there are two surfaces, and so there are two edges. If you're in the correlated phase, where the regions are close enough to each other so that the minimal surface for the AB would be this arch, then this arch would contribute another region that's separated from the rest of this bulk. And so there would be an additional vertex and edge. And so when you have a entanglement entropy of a subsystem, it's computed by a min cut where, okay, so each edge, I should have said, each edge has a weight associated with it that corresponds to the area of the surface. And the min cut is just the cut through the, such that the areas, the combined areas are minimal. So if this surface is smaller than the sum of these two surfaces, then on this side, we would have a min cut through this edge corresponding to this surface rather than these two. But we can also incorporate the decorrelated phase even on this more general diagram by just taking a min cut through these edges. So it depends on what are the weights on these edges. In other words, what are the areas of these surfaces. Okay, so that was already developed a while ago. So that's the toolkit that we want to use because it's this nice, convenient, discrete structure. We don't have to worry about this UV divergences and so forth. Okay, so of course, graphs that correspond to actual configurations can get awfully complicated. So already for n equal to 4, if you have a set of 4 regions that are correlated with each other pairwise, and therefore correlated in larger systems, then the graph corresponding to that is a total mess. Because you have all these arches and then all these 3-legged arches and they all intersect. So they intersect in sort of 43 separate regions. And so that gives you 88 pieces of RT surfaces. So instead of such graphs, we can actually use simpler graphs. Okay, and that's quite remarkable. Yeah.
Sorry. Can you go back a couple of slides to the one where you introduced the graph? Yeah. So here, so suppose I try to think of on the right graph, suppose I try to think of the vertical bit from the purple dot to the P as kind of the mutual information. Okay. This
thing.
Yeah.
Mm-hmm.
Like if you thought about
the mutual information is like this weight minus this weight minus this weight.
Yeah, right. So
rather the opposite.
Oh, I see. I think that is that way. Okay, let me rephrase my question a different way. In the big graph you drew, does it contain all possible topologies of RT surfaces? The big graph you drew in the next slide.
No. Sorry. No. So this was meant to be what you would guess for vacuum state, for pure ADS. So you have some inkling of what these surfaces look like.
Right.
If you had some excited state that sort of deform the surfaces, then you could in principle have well, okay, actually. I think it, okay, I don't think it would get more complicated because no matter how you deform this, the entanglement wedges would nest.
Right.
So it might not be any worse than this. I should think a little bit more about it, but okay.
I see.
But you could get topologically complicated looking surfaces. They could have holes and whatnot. But I think this.
Oh, right, yeah. Holes apart, like somehow we forget about holes. Does it contain all the topologies here? Like all the ways in which A, B, and C can be connected, A, B, C, A, and D can be connected, and so on.
Yes. Everything is correlated with everything else, so it contains that. Yes.
Okay, thank you.
Yes. Was there a reason you were asking, or this answers?
Yeah, I was just trying to understand what this graph really is, and I guess the point, okay.
I'm not going to use it for anything. So the point of the next slide was that you don't actually have to deal with this mess.
Yeah. So thanks.
So it's more to say, you can breathe a sigh of relief that
Okay.
you don't have to understand anything about this.
Okay, thank you.
So what are the nice things? So I'll motivate why are tree graphs relevant in a moment. Let me first make the observation that they're nice. Okay, so tree graphs have the structure that they don't have any of these cycles in them, which means that that corresponds to not having RT surfaces that would intersect. So the entire collection of RT surfaces that get activated when you calculate subsystem entanglement entropies for all subsystems give you a bunch of RT surfaces. They could have all sorts of topological structures, but none of them pairwise intersect. Okay, that type of configuration would give you a tree graph. And so each edge in a tree graph can be specified by a unique collection of boundary vertices up to taking the complementary set. Okay, we can isolate one set as not preferred by having this purifier, and okay, so that gives us this unique set. And the pattern of marginal independence then follows from specifying directly what is the min cut. Like if you have a min cut for BC that goes through this edge, then you know that B and C are correlated, whereas if it goes through these two edges, then they're uncorrelated, and so forth. Okay, now, so a graph we call simple if each edge defines some subsystem cut, like this edge defines the BC cut, which equivalently means that each boundary vertex has its own different name, different color. So if this was B and this was B, and I cut this single edge, then that single edge would not be homologous to B region, and therefore it wouldn't have specified this subsystem cut. Okay, so ultimately, the result that we'll use pertains to simple trees. Now, how do we get to simple trees? Okay, so let me make one more observation about why simple trees are good. The point is that for simple trees, it's pretty easy to show that the V space actually is the PMI. So here is our nice context where we made contact between the V space, which knew all about the multipartite entanglement structure, and the PMI, which only knew about marginal independence. But if you have a simple tree like this, then the two are equivalent. The reason the two are equivalent is that the restrictions from the entropy space that delimit the subspace, that is this, are always in the form of, some entropies specified in terms of some other entropies. And what that means in effect is that if you say like the BC entropy is really B plus C entropy or something, it always boils down to have a form of subadditivity saturation or hierarchy leap saturation. And therefore, and that's the thing that the PMI knows about. Okay, that's why the two are equivalent. Okay, so simple trees are nice. Our holographic graphs are awful. So what do we do for the holographic context? So the so everything now we do rests on a conjecture. We don't yet know how to prove it. We have plenty of evidence for the conjecture, but so far the point is just taking it as a conjecture and saying what are its implications. So the conjecture is that in fact we can convert any graph model that's holographic into a tree graph. So far not a simple tree graph, just a tree graph, while preserving the V space. So for example, the entropy vector, in particular, we're preserving the entropy vector. So if you have three subsystems described by this graph configuration with these edge weights, it has identical entropy vector if you have this tree graph. In fact, this one is a simple tree graph because all of these things are different by the colors mean subsystem color, and okay, all of these are different. So we've converted something with a cycle to something that has a tree. So we have plenty of examples where you have some more complicated cycles that you can convert into a tree and so forth. And in fact, you can show explicitly that for all the known extreme rays graph representations, you can indeed convert them to tree graphs. Okay, and there will be one more step to make them into a simple tree graph. But for now, just to illustrate the tree graph, this is taken from Sergio's paper on the n=5 holographic entropy cone. So these are the explicit graph representation of all the 19 extreme rays. And you can see that some of them are not a priori trees, but all of them have the feature that, for example, if you take this cycle, you can actually split this boundary C vertex into two boundary vertices and open up the cycle. So you can do that with everything. And there are simpler sort of graph representation for this where you can't do it so naively. So you have to use more complicated sort of graph moves, but nevertheless, you can make all of them into trees. So, but they're not simple. So if I do this trick of splitting a boundary vertex, I have a boundary vertex now of with the same color, two distinct boundary vertices with the same color. So it's not a simple tree. So the next ingredient comes into making it into a simple tree. So that goes to this other tool, which is the fine graining and coarse graining. They're just reverses of each other. So they pertain to changing the number of subsystems, so which simultaneously changes the dimensionality of the entropy space in this exponential. Remember, this is 2 to the n minus 1. This would be 2 to the n prime minus 1. Okay, so it's a large change. But various aspects of the entanglement structure get preserved in this fine graining and coarse graining. So coarse graining just simply declares two what used to be distinct colors as indistinguishable. Okay, and that means that a whole bunch of entropies are in effect the same, and so it effectively projects the entropy vector in this space to this space, and correspondingly projects the linear subspaces, the V space and the PMI. The reverse of this is to distinguish colors. So when we had two edges going to a C vertex, I can say, well, this one is really C1 and this one is really C2, and they're really distinguishable. And I don't know a priori from the original specification what the different edge weights would then have to be. I just knew that combined sum. But if I recourse grain, I get back what I started with. So the fine graining, of course, is putting in extra information that I have to specify, like any fine graining. But if I recourse grain, I get back the same structure. Okay, so crucially, I can now obtain the simple tree graph, which is the one that has V space being the same as PMI, by fine graining, sort of trivially. Okay, so the main upshot of that procedure then is the following. So we'll consider the extreme rays of some N-party holographic entropy cone. And of course, the full holographic entropy cone is the convex hull of those, all of those extreme rays. Okay, and so once you know the extreme rays, you can determine the cone, and from that you can determine the inequalities if you want to have that sort of polyhedron representation of that holographic entropy cone. Okay, so we assume that if we know the extreme rays, well, then we can determine all these inequalities. We can determine the cone and we can process it any which way we like. Okay, so the theorem is assuming this conjecture that we can convert any graph to a simple tree, then every extreme ray of the N-party holographic entropy cone is actually obtained as a projection of an extreme ray of a subadditivity cone. Just the one determined only by subadditivities, none of these unknown holographic inequalities, but for some larger number of parties, for some n prime parties. Okay, so that's the statement. The statement is all we need to know is subadditivities, which we do explicitly. From all of them, we know what the cone is. We can extract the extreme rays, okay? But we have to figure out which extreme rays. Okay, that will be the crux of this. But any extreme, well, conversely, any extreme ray can be obtained as projection of some extreme ray of this subadditivity cone. All right. So how does that follow? Well, the rough idea of the proof is, well, you start with this holographic entropy cone for n parties. Okay, you have some graph representation G, and because it's an extreme ray, it's one-dimensional. It has one-dimensional V space. So far, we don't know anything about PMI, but it has one-dimensional V space because it's an extreme ray. Now you use the conjecture that you can convert it to a tree graph, and then fine graining to convert it to a simple tree graph. Now that simple tree graph lives in n-prime dimensional entropy space, but because it's a simple tree graph, its V space is actually a PMI. It's a PMI now in this d-prime dimensional entropy space. And you might have picked up dimensionality in this fine graining. So far, that's not necessarily an extreme ray of the subadditivity cone. It's some phase of the subadditivity cone because it's a PMI. But you can then use the additional freedom you have in having fine-grained to reduce the dimensionality down to a single dimensional, down to one-dimensional subspace. And so you can get down to a one-dimensional PMI, and because it's a one-dimensional PMI, pattern of marginal independence, it's an extreme ray of the subadditivity cone. And so now you can project down, and that gives you the proof of the statement of this theorem. Okay, so let me now go to the, well, let me say first whether there were any questions on this. Before I go to the implications. Okay.
Sorry, so when you simplify the graph into a tree, so are coarse graining and fine graining the only moves you have?
Sorry?
Are coarse graining and fine graining the only moves you have to simplify the graph into a tree?
No. They're the moves that I'm using to convert a non-simple tree into a simple tree.
I see. Okay. What moves do you have for the first step then? To make it into a tree?
I have various moves. So I have, I don't know if you can you see this, or is it too tiny?
Oh, sorry, I didn't realize this. I
didn't say this, but this is an example. Okay. So you can take two, if you have the same color vertex, you can combine the vertices to get a piece like this, or you can split it, that was the move. One was what I was using, but you can do a bunch of other things. Some of those were already described in the entropy cone paper. Some of them are new, and there's more such moves that we're using. So you can collapse cycles and so forth. So we haven't really determined what are the atomic building blocks from which all the necessary graph moves are. So this would be part of the proof of the conjecture. Okay, so we have gone some way, but not entire way. But we have enough to convert all the extreme rays that we know of. One thing that's curious, by the way, is what we don't know how to convert doesn't occur just phenomenologically, empirically doesn't occur in extreme rays, but things where you have cycles that adjoin in some, that are multiply adjoining. If you're just two cycles that adjoin each other, it's okay. But if those two cycles are simultaneously adjoined by another cycle, then if you sort of collapse one cycle, then it goes the other ones. And we don't know how to how to get around that, but we don't seem to need to for the extreme rays, but we don't have a proof that
Okay.
it can never appear in extreme rays. So that's where that conjecture stands at, and that's why we're calling it conjecture.
I see. Thank you. And one more question I had was about just the definition, just the statement of your theorem. What does it mean to say that the extreme ray of an N-party cone is the same as the that of a subadditivity cone for an N-prime party system? Because
Right, so
these are cones in different vector spaces, right?
The cones in different vector spaces, it's a projection. So you project the large dimensional vector space,
Okay.
subspaces of that, down to just this d-dimensional, the thing that pertains to the original N.
Is there a unique projection? What is this is, yeah, good. What is the unique
Very good. So there are multiple projections. But you can get any one of, well, okay. So if you have the entire orbit of, all the extreme rays, then you can just decide on one specific projection, and you always hit it for some extreme ray of that orbit. Conversely, you could have considered a whole bunch of projections to build up the entropy cone.
I see. So you're saying the choice of projection is it's just some permutation choice.
Yeah, exactly.
Oh,
because the whole cone, I haven't said this explicitly, the whole cone is permutation symmetric and purification symmetric.
Okay, thank you.
Okay, Veronika, just a thing about the time. Maybe we can conclude. We are at 3:15. So maybe we can conclude, and then people who want to leave can leave, and the interested people can stay for discussion.
Okay, how quickly should I conclude? How many minutes?
5 minutes.
Sounds good. Okay. So the implications, I have only 2 more slides. So the implications then is that the holographic entropy cone for some N-parties is fully determined now from knowing just the subadditivity cone, but for a larger number of parties, where I haven't told you how N prime is related to N. But the curious thing is that this really bounds all quantum states regardless of holography. This doesn't know anything about holography. In fact, the quantum entropy cone is well within the subadditivity cone, because the quantum entropy cone also is delimited by additional inequalities like SSA and so forth, which this one doesn't know anything about either. But nevertheless, the extreme rays that we have are sufficient to reconstruct this holographic object. Okay, so that in some sense maybe demystifies the holography, maybe mystifies it, because it sounds like it's like almost a free lunch. And this goes back to the comment I made earlier, that somehow I think part of the lesson here is that maybe holography isn't all that special, apart from the fact that you have this continuum on which the field theory lives, and you can partition it spatially, you can partition it in any which way. And that may be the operative part. But this is wild speculation. The result is this, and I'm not fully sure what to make of it, what narrative to accompany it with, but that's the upshot. Okay, so similarly, all sort of faces, the intermediate dimension bits of the boundary, and internal such things like spans of various other extreme rays are of the holographic entropy cone are just projections of the various faces of the subadditivity, larger and subadditivity cone. And so now all our complicated multipartite entanglement structure is really rooted in just this marginal independence, in the pattern of marginal independence for a more fine-grained system. But nonetheless, the non-subadditivity facets of the holographic entropy cone were shown to have a property that we call superbalance, which, well, okay, due to lack of time, I won't specify this further. You can ask me questions about it, but what it implies, okay, this is work in progress with Frederic Gia and Sergio Hernandez Cuenca, is that they can't be correlation measures. They can't be monotonic quantities, even though they originate from something that only knew about correlation measures, only knew about just simple correlation, which was mutual information. Okay, so this was one set of implications. Now, in practice, if you were to construct the holographic entropy cone for some arbitrary n, then that's, of course, in practice complicated, because you have to know, well, first of all, which extreme race you want to take. And then you have to project, you have to take the convex hull, you have to extract the extreme race, and then reconstruct the facets and so forth. Now, but conceptually, this sort of slightly demystifies the construction. So the next step is to figure out, so which extreme race of the SA cone are the correct ones to take? And this gets us back to this marginal independence problem. And we conjecture that, in fact, any extreme ray of the subadditivity cone that's compatible with quantum mechanics is actually sufficient, is holographic, because that, and it's therefore that's precisely the set that we want. Now you might speculate that even though the quantum entropy cone is delimited by more than just subadditivity and SSA, the SSA might actually suffice to delimit the set of extreme rays of the SA cone that are required. In other words, all these other restrictions that restrict the quantum entropy cone don't touch the extreme rays, and therefore SSA might be enough. And if that's the case, then the statement would be very simple. The holographic entropy cone would just follow from knowing all the subadditivity extreme rays that are compatible with SSA, which is something that you can imagine really doing, running an algorithm to just generate the cone for the end. You still will have this exponential explosion, so it still would not be practical, but for larger, for n more than some, 7, 8 or something. But nevertheless, we know conceptually where it comes from. We would have the full mathematical definition of the object. Okay, so let me end here.
Thanks, Veronika, for the very nice talk. Any further questions?
Yeah, I have one more. Yeah, sorry, can you, so how do you convert the perfect tensor entanglement into subadditivity of some higher number of parties? Can you just, do you know the offhand how it works?
Yeah, so basically you want to
like the 4-party perfect tensor you showed us.
Right. Let me think how many.
Sorry, if it's hard, it's fine again.
Sorry, I have to think about this a little bit more.
Sure, yeah.
What I can tell you is a slightly related thing. If you have one of these holographic configurations that generate the V space being different from PMI by having, for example, saturating the tripartite information, you could fine grain it. So let me actually see if I have a corresponding picture here. Okay, I don't have a picture here. Okay, it involves the generating configuration would have involved 3 colors, but really 6 regions. And there it's easy to see that configuration, actually, if you declare all the regions to be distinct, So you uplift from n equal to 3 to n equal to 6, that the fact that you have saturated I3 being 0 now uplifts to just saturating I2s, and you really see that now in that configuration, the V space is the PMI. That doesn't answer your question. I should think about locally it should be very simple to answer, but locally I'm blanking out. So let me see if there are other questions, and then I'll try to rethink about this.
I have maybe just a naive question. So as you said in the beginning, all this was strictly in the classical limit at infinite n.
Yeah. Yes.
If we include quantum corrections, for example, if I can take a GHZ state in the bulk, is it clear that these entropies will have versions that apply with 1/n corrections? I said
No.
GHZ state in the bulk because you said the MMI is violated by the GHZ state. So yeah.
No, that's a very good question. So it's not clear. In fact, I think much of what, I mean, the whole structure is really very hard-rooted in the classical limit. And it's not clear what part of it really, survives in any useful way for quantum correction. So first of all, you can naively get outside of the cone, as you say, by, for example, violating MMI. On the other hand, you're forced to be sort of inside the cone because you can't saturate subadditivity because mutual information is bounded from below by a correlation which doesn't vanish if the space on which the CFD lives is connected. So the whole structure, I mean, certainly it's sort of, I mean, I picture it as being sort of more fuzzed out. If you have just some 1/n corrections for large n, it's going to be maybe fuzzed out at that commensurately small order. But I don't know how to utilize. See, the classical limit, what it allowed is really extracting this discrete structure. And that was crucial in, we have sort of stopped caring about what is the actual entanglement entropy value, but really cared only about this structural aspect of the density matrix. I don't know how to do that outside of this regime where you don't have this set of quantities that are sort of cleanly saturated.
Okay.
Yeah. So maybe the slogan, I mean, the whole point, the whole motivation was sort of trying to understand the entanglement structure of geometric states in holography.
Yeah, no, I understand. That's why.
Yeah, but that's well, it might be, you can view it either as a limitation, well, either as a bug or as a feature. But in any case, it's I don't think it's very, I don't know how to extend it.
I guess, is it true that initially this inequality was because people were looking for, can a geometric wormhole capture a GHZ type entanglement, and then MMI would show that at order n squared, you can't have that, right? For example.
Correct.
So in that sense, it's useful. I was just asking a question about the quantum corrections separately.
Yeah, I mean, one would have thought that generically, I mean, it should be a larger cone, but I mean, there's a nesting, right? So the SA cone is the largest thing. Then you could have SSA, reduced SA cone where you only keep, well, sorry, let's say SSA cone where you keep SAs and SSAs. Then smaller structure is the quantum entropy cone. Even smaller structure is the holographic cone. Well, an intermediate one is this graph cone or area cone where I don't worry about all possible, well, okay. So to go between graphs and these holographic configurations, you can always sort of think of the graph as given by some geometry configurations where you, roughly speaking, you can blow up the edges and think of it as a geometry, and each edge is the sort of the neck of the geometry. But the problem is you don't know that thing is holographically. I mean, it's some okay geometry satisfying Einstein's equations, but you don't know whether that's the geometry that dominates if you take the CFT, the corresponding CFT state. So in that sense, it's what some people call the area cone rather than the holographic cone. So this area cone could be larger than the holographic cone, and we don't really know how to tell, whether it is or how much more restricted the holographic cone might be. So when I was talking about holographic cone, I really, strictly speaking, meant only this area cone. That can then be shown to be equivalent to this graph cone.
Mm-hmm.
But there's this hierarchy. And somewhere sandwiched in this hierarchy is so I also was talking about just the static context where RT applies, because that's the context where we can use these graphs. So HRT cone, I think, but it certainly would be no smaller than the RT cone. We think it is equivalent, but now we can't use the same toolkit. So we have sort of other arguments to say that, I mean, if you think in terms of these proto-entropies and define the cone as the polyhedron, then it's pretty clear that the proto-entropies, which are just the HRT surfaces, all that counts is which ones are activated when you're looking for the entropy vector. And that question is the same for static context and dynamical context. And so we think that the polyhedron the RT polyhedron is identical to the HRT polyhedron, and therefore, it's all going to be the same cone. But it's another thing that's, another structure that you might have said is a priori distinct from the others.
I have one more question. This is the last one, sorry.
But
this result that you can always, you can take an extreme ray on the holographic cone and fine grain the subsystems to make it just subadditivity. It's somehow reminiscent of this mostly bipartite conjecture by, I think, Hayden and Hedrick. I forget the exact authors, or maybe Maloney was there, which basically says that you can just think of any holographic entanglement structure as taking bell pairs between all the subsystems and scrambling them separately in all the subsystems separately.
But it's only for the n equal to 3, right? It's only
n equals 3. Yeah, that's right. Sorry.
Yeah. So what was the question?
Yeah, sorry, I didn't mean to say it was for everything. Yeah, that's right.
So then it's harder to make connection with my context.
Oh, I see a point. Okay, I see.
But you see that I mean, one thing to say is that if you diagnose multipartite entanglement by this multipartite information, so there's a tripartite information, four-partite information, and so forth.
Yeah.
Those are constructed from entanglement entropies, and you can rewrite them as just combination of mutual informations now between not single systems but composite systems. Okay, so just like I have gone with the I3, I have determined it in terms of the I2s, right, at the very beginning. So sorry, not here. So you can do it for here. So this object is written purely in terms of mutual informations. You can do that with all the higher ones.
Right.
And so then it's not, if you know the sort of mutual information between anything and anything else, you really do know the multipartite entanglement structure, even though you're describing it only in terms of mutual informations. So maybe one lesson is that, we're saying mutual information that just knows about this bipartite correlation, but having bipartite between anything and anything else does amount to this multipartite.
I see.
Especially when the anything and anything else is overlapping. Sorry.
Right.
I mean, the collection of them is overlapping.
Right. I see your point. So the reason I was asking about this way of writing down the state is that there is this tension where the existence of a non-zero reflected entropy seems to be seems to be in tension with this mostly bipartite conjecture of these guys. This is a paper by Akers and Trust, and I was wondering whether there was a way to think about reflected entropy in this story, and
Yeah. Okay. Actually, I just realized the answer to your previous question. I'll tell you the answer to the previous question first, which is which is that if you have the four-party perfect tensor, that actually saturates all the mutual informations. So that is an extreme ray of an SA cone already for the same number of parties, and then therefore it's consistent with already being a simple tree graph. Okay, so it was too simple. Okay, good. Now this reflected entropy, you copy the system. And you don't find, I mean, it's not really fine graining in the sense that you're not allowing yourself to have the freedom of dealing with the subsystems. So a priori, I don't know of there being a sort of a direct connection.
Okay.
But I mean, maybe there is some, I mean, it's a nice context to think about. So maybe there is something nice to say. I just don't know. I haven't thought about it. But nothing is sort of, it's not apparently, I don't have anything immediate to say.
All right, thank you. Yeah.
Can I ask a question?
Mm-hmm.
Hi, Veronika. So if you have, once you determine those holographic entropy cones, but I can trying to construct those states using tensor networks, right? And it may be happy code or other type of code. Does it so the idea will be those cones will construct what type of tensor network you can use to represent holographic theory, like geometric states.
Yes.
Right. So is there in the case where n is small, are there simple thing to say about what's the structure of the tensor network that will be that will obey the cones, or a generic tensor network will just obey those entropy cones?
Well, do you know how to extract what the tensor network gets restricted by in terms of this?
Well, that I don't know, but the only naive thing you can think is by trial error, thinking special type of structure of tensor network and simulate it to find if it's satisfied. But maybe another question is
I mean, you can ask in some sense, well, anything that obeys RT manifestly would be
but not
the requisite entanglement structure. It's almost a sort of tautology.
But not all tensor network obey RT. They are bounded by RT, right? The entropy is bounded by.
So RT, then the question is, okay, so you could okay, so instead of asking, do they obey all the holographic entropy inequalities, which would have been guaranteed by RT, of course, but this would be, they could obey them even if they don't obey RT. One could ask whether the reformulation in terms of the subadditivity cone for fine-grained system
Mm-hmm.
is more convenient to use. That would, if that's the case, that would be an application of what I said. It's not obvious to me that would be the case for the tensor networks.
Well, yeah, the question appears to me because since you are interested in the limit where you like partition the system to be like a large amount of copies, so you can effectively think about each small system you divided is like some outgoing legs in the tensor network. Then it seems what you are trying to do is trying to like get in some structure of this tensor network, some coarse-grained bound out of structure.
Correct.
That's what
and in principle, I mean, in principle, this N prime that I was using could be fairly large. So if you look at this extreme rays, and you take each boundary vertex and you split it such that you get a tree graph, and then you make all of them distinct so that you get simple tree graph. That drives up N prime to be, like twice N. Now, you don't need to go to that length for N equal to 5, but for larger N, it's not guaranteed. We're not sure. We have an upper bound on N prime, but it's sort of useless upper bound because it's sort of exponential in N or something. So it's not a useful upper bound. So for tensor networks, it might turn out that the requisite N prime would already be more than the thing that the system could accommodate. That's one danger, but maybe it's not. I mean, and again, for small n, the N prime doesn't need to be a whole lot bigger than N. So that worry might not be relevant. In which case, you may be right that this would be a more convenient way to ask about the tensor networks. Again, this is something I have not at all thought about. So I don't know.
Yeah, it just seems like you're getting some structure. I mean, yes. I wonder what's the relation to the structure of tensor network being described.
That's certainly a nice question too. It's a very nice question.
Yeah, thank you for the question. Sorry, thank you for the answer.
I thank you for the question.
Okay. Any final questions? Okay. If not, let's thank Veronika again.
Thank you. Yes.
Thanks, Veronika. That was a very nice.
Yeah, very nice. Thanks.